Hello, I'm Dr. Yung. Today I'll present to you a review on heating and cooling mechanism for SMA actuator. Today's presentation will cover an introductions, followed by the working principle of SMA, then the review of resisting heating with natural and forced cooling. We'll talk about also laser heating, and followed by the thermoelectrics module heating and cooling. We also discuss a bit on the liquid heating and cooling that used together with the thermoelectric modules. From there, we propose the optimization of silicon and encapsulated SMA, and a conclusion will be drawn. So SMA stands for shared memory alloy. It's a type of alloy that you can see here are some of the examples of this alloy available in the markets. Yeah? So to increase the strength of the alloy, most of the SMAs are made into spring coil shape, yeah, to extend the strength of this material. Yeah. So the applications are widely used in robotics as artificial muscle, and also some are used in dental use. So the SMA, they are thermomechanically behave. Yeah. So when you heat it up, the SMA, it will change to cubic crystal structure, which is very strong, and when you cool it down, it will become monoclinic structure. Yeah, and they can change to detwin and twin structures. Yeah, so in or so-called the Martensar phase. Yeah, in Martensar phase, the SMA are soft, are easy to deform. You can make it into other form. When you heat it up, yeah, the molecular structure change back to cubic crystal, and the stress increase in the molecular structure realign the shape of the alloy back to the program shape. So it exhibits a kind of memorizing the initial shape. Yeah. So to program the shape, basically we will hold the SMA into the form or into the shape that we want, and we'll heat it up to a temperature ranging from 350 to 600, then followed by a quenching process. Then the SMA will be basically programmed to the particular form, and whenever it's heat up, then it will tend to reform back to the program shape. Yeah, so that's why you call it the shape memory alloy. Yeah. So to control the shape of the SMA, basically we need to control the heating and cooling. Yeah, because they are mechanical behavior. So the most used method are basically the resisting heating. So just supply currents to the SMA, and the resisting heating will generate heat to heat up the SMA. Yeah. So basically the SMA in form of wires or spring coil wires. However, these methods are only heating. There's no cooling. Yeah. So some of the researchers is based on natural air cooling. Yeah. So but the cooling process is slightly slow. So air force or active cooling method using fan are also been investigated by many researchers. However, the cooling methods using air force difficult to be controlled. Yeah, although it's much faster than the natural cooling, but it's uncontrollable. So to better control the active cooling process, some of the researchers encapsulate here the semi wire so that they can control the precise of amount of air, yeah, into the area, yeah, between the SMA and the encapsulation. Therefore, they can cool down the SMA in the manner that they want. However, these methods still need improvement because the cooling process is still difficult to be controlled. Some other more precise heating methods are, for example, using the laser heating. The laser can be, the intensity of the laser can be controlled. Therefore, a right amount of heat can be generated on the SMA. However, such a technology are basically used in a very small piece of SMA. Yeah? So researchers are still limited to the size of the SMA by using the laser heating. By looking at the SMA heat manipulation, basically we need both heating and cooling. So the thermoelectrics modules, TM, actually have both the function to provide heating and cooling at the same time. Yeah. So this is a TM for LED technologies. So when you supply current from one side to other side, you can create heat on one side and cool from the other side. Yeah. So the TEM is basically acting like a heat pump. It will pump the heat from the cold side to the hot side. Yeah. So if you reverse the current polarities, basically you reverse the hot and cool side. So the bottom side now will be cool and the top side can be heating. So basically you can use the TEM to control the temperature, yeah, of the SMA both in terms of heatings and cooling. However, as you can see, this is the market available TEM you have is basically made of two pieces of ceramic sandwiching the uh, TM material in the center. So the physical structure is basically very rigid, and therefore only flat surface or straight SMA are able to use to be contact with the TEM. Yeah? So these geometrical constraints have limited the shape of the SMA that we can use with the TEM. However, the shape of the SMA are important to allow larger strain, larger usable strain for the SMA. So this is why most of the SMA now they are forming them into coil shape or kind of that to increase the strain. Yeah? So overcoming the setback of the TMs, and researchers are using liquids, yeah, to harness the heat and cool from the TM and channel to the SMA in a encapsulated environment. Here you can see a bundle of coil spring SMA inside the encapsulation. Yeah. So hot and cool water can be channeled into the encapsulations to control the temperatures of the SMA. So therefore, we can control the mechanical behavior of the SMA. However, these methods are still in the early stage of the investigations. So there's no intensive finding to support what is the best membrane thickness and the gap in between the SMA, and also the limitations where you have the bundle of SMA in a large area, a large volume. So therefore, lots of cool and hot water need to be supplied to the chamber to heat and cool the SMA. This will reduce the response time of the SMA actuator. And some of the researchers use tubings to encapsulate the SMA. However, the tubings thickness and elasticity and also the gap could affect the performance of the actuator. So with that, we come out with a curve shape SMA design, with encapsulated by silicone as a membrane. So here we see the needs of a study to study the gaps and the thickness the gap between the SMA and the membrane and the thickness of the membranes to optimize the performance of such a actuator here, because the gap will define the amount of liquid that we need to supply to fill up the whole content, to change the temperature of the SMA, and the thickness of the membrane basically will affect the movement of the SMA and also the insulations of the uh, heat inside the encapsulation from releasing to the environment. Yeah? So with that, we can see the extensively used resistive heating having too much of setback. Yeah. So the use of TEM also hindered by the geometrical constraint, and the use of tubings to solve the TEM has not been properly studied. So therefore, in this research, we aim to formulate a method to fabricate the silicon encapsulation for the SMA. At the same time, we would like to optimize the thickness and the gap of the silicon encapsulation. Okay, with that, thank you for your attention.